go to the, it's a video on squares, square of a Vedic math way. It's video number 12. It's a video on squares, and we will square of numbers, integer numbers. It's Vedic math way, video number 12. Let's continue. Do squares in various sections. First section is as observed by Shkuta Devi, and the book we are using here is her book Figuring Joy of Numbers. Let's continue. Then we will have section on numbers ending in 5. Next section would be using base multiplication method. Next number would be using formula, and then we will use duplexes, which comes from vertically and crosswise multiplication method. So we'll use, first section is observations as made by Shkuta Devi, and reference book is here, figuring. Then we have section on numbers ending in 5. Then we have section on using base multiplication method. Then we'll use a formula again, then use a duplexes. Okay, let's continue. So here is sum of odd numbers is the first observation that Shkuta Devi makes in her book. So that's in Taste of Sutras, we had observed that sum of odd numbers starting from 1 is square of numbers of the array terms. We had used the by completion to compute that. Okay, so we use the sutra by completion to compute a sum of odd numbers starting from 1, and we had found out that was a perfect square. Let's continue. So Shkuta Devi starts with the same observation. Thus 1 is equal to 1, which is the square of 1. Next is 1 plus 3 is a 4 with the square of 2. So add 5 and 3 of those, 3 odd number, 1 plus 3 plus 5 is a 9, which is a square of 3. Then add one more digit here, 1 plus 3 plus 5 plus 7 is 16, which is a 4 square. And add 1 plus another number here, 1 plus 3 plus 5 plus 7 plus 9 is 25, which is a square of 5. And note 1, who is Shkuta Devi? Please check out the Wikipedia entry at http://n.wikipedia.org/wiki/Shakuntala_Devi. Let's continue here. Comment. From now on, the video will use she and her to imply Shakuntala Devi, and all these observations are from her book Figuring the Joy of Numbers. Let's continue. So we'll continue with sum of odd numbers. Okay. For the smallest square, we need one tile. If you're trying to fill up a square with tiles, so one square is 1. For the next largest square, we need to add a row and a column of 2 tiles each. In this added row and column, one tile is common, and thus added tiles are 2 plus 2 minus 1, which is equal to 3. That means for next square, I need to add 3 to get a next square. Okay. Total tiles laid out so far are 1 plus 3 equals 4 and 2 square. Did you notice that we added an odd number here? Okay, let's continue here. Now all the tiles are square, disjoint, no overlap, and of exactly the same size. You must recall puzzles like how many squares in a figure. Okay, let's continue. So it's all the tiles are of the same size, they're all square, perfect square, and they're laid down one next to each other, adjacent to each other, and they are disjoint, there's no overlap. That's about okay. So for next largest square, lay down another tile row and column of 3 tiles each with one common tile. Thus we would add 5, the next odd number tiles. Okay. So then 1 plus 3 plus 5 equal 9, which is 3 square. Let's continue. Extending of the square continues by laying down odd number of tiles. Okay, that's our book has a square number here. Continue. Square number is a number of square tiles in a square. By definition, that is a perfect square. Okay. Further, that is given by sum of odd numbers. Numbers starting with 1. Okay. A square is given by sum of odd numbers starting with 1. Let's continue here. The square of n is 1 plus 3 plus 5 plus 7 plus 2 times n minus 1 term. Let's continue here. The series of a right is sum of odd numbers starting with 1. Let's continue here. Triangle number here. The book has a concept of triangle number, which is number of square tiles in a triangle at a corner or maybe vertex of a square, okay? Of a square of tiles. Let's continue. Note, I have not, to admit that I have not seen or heard of this concept of a triangle before. I have run into Pascal triangle and Kepler triangle before. And Kepler triangle is right angle triangle with sides of 1, square root of phi and phi, okay? And this phi must be, okay? And from Pythagoras theorem, we know phi square is equal to phi plus 1, and that means that's the equation of golden ratio. Phi must be a golden ratio. Let's continue. For triangle consisting of single row of tiles, triangle number is 1. Square of 1 is also 1, and triangle of 1 is also 1. Let's continue here. For triangle consisting of 2 rows of tiles, which have a triangle number is 1 plus 2. 1 the this one row has 1 tiles, and the next row has 2 tiles. 1 plus 2 is 3. Okay. So triangle consists of 3 rows of tiles. Triangle number is 1 plus 2 plus 3, which is equal to 6. So triangle of 3 is 6. So triangle of n is equal to 1 plus 2 plus 3 plus so on up to plus n. Observation. She has observed that triangle number times 8 plus 1 is a perfect square. Let's see what's going on here. Analyze. Triangle of n is equal to 1 plus 2 plus 3 plus so on plus n. And if we complete 1 plus n, we would have a n by 2 pairs of this type, 1 plus n. And that means triangle of n is 1 plus 2 plus 3 plus so on plus n equal to 1 plus n times n divided by 2, which is equal to half of n squared plus n. Let's continue. Some of you would question, if n is odd, how would we make n by 2 pairs? Okay. In that case, if n is odd, n plus 1 must be even. Okay. Then we can use an alternate form to compute the sum of a natural numbers starting from 1. Let's continue. So triangle of n would be, in alternate form is average of 1 plus n, which is the first term and last term here, and times n. Okay? Instead of doing n by 2, we are doing n here, and first term is average of the first sum of first and last term, okay? Which is equal to half of 1 plus n times n, and that is equal to half of n squared plus n, just like we did before. Okay? The observation, and apply her observation that triangle number times 8 plus 1, which is equal to half of n squared plus n times 8 plus 1, which is equal to 4n squared plus 4n plus 1. Okay? And if you try to get a groups of 2n plus 1, okay, let's see what's going on here. So that means if I say get 1 equal to 2n groups of 2n plus 1 and plus 2n plus 1. Okay? You split that 4n into 2n plus 2n. One of the will combine that 2n will combine with 4n squared, and other 2n will combine with 2n plus 1. So here are 2n groups of 2n plus 1. Here is one more group of 2n plus 1. Okay? That means we have 2n plus 1 groups of 2n plus 1. That means the left hand side is equal to square of 2n plus 1. Let's continue here. Which is square of 2n plus 1. Okay, so that's what the observation was, that is perfect square. Let's continue here. So triangle number of n times 8 plus 1 is a perfect square. We just analyzed it, proved it, that it so is true, and that was the observation Shakuntala Devi had made. Let's continue. Squares from triangle number now. Let's continue here. So we claim that sum of odd numbers starting with 1 is a perfect square. Okay, that we already know. Okay, and you can prove that. I had proved that when I first learned of that in high school. So that I know for true. So I did not go through the analysis here. Okay, let's continue here. So n is equal to 1. Then triangle number 1 is 1, and when I multiply that by 8 and add 1, I got 9, which is square of 3. Okay? So triangle number 2 is, so it's a t of 2, which is a 3, and when I multiply that by 8 and add 1, I got 25. That's it. I got 5 squared. Okay? So when do n plus equal 3, I got a triangle of 3 is a 6. Multiply that by with 8 and add 1, I got 49. So I'm getting, what I'm getting here is sums or square of odd numbers. Okay, we said 2n plus 1 squared. 2n plus 1 is a odd number. So when n is 1, 2n plus 1 is 3, so that's 3 squared. When n is 2, 2n plus 2 is 2n plus 1 is 5, 5 squared. And when n is 3, 2n plus 1 is 7, that's 7 squares. Continue here. N is equal to 4, t of 4 is 10, triangle of 4 is 10, which is 1 plus 2 plus 3 plus 4. And when I multiply that by 8 and add 1, I get 81, which is a square of 9. Let's continue. That's the square of numbers ending in 5. Okay. She treats this number in same way we treat these numbers in Vedic math. The two methods are functionally equivalent. Okay. And you can look at this video here, proportional base multiplications for the way we use this, do square of numbers ending in 5. Let's continue here. We will discuss these squares in a later section. Okay, so Kunta Devi uses the same method as we do for the numbers ending in 5. Trying to get a square of numbers ending in 5. The method is functionally equivalent, and we will discuss that in a different section. Okay, now square of sequence of 3 is the Kunta Devi has observed that a special pattern in these squares. Okay, so 33 square is 1089, so 10 and 89. Two parts are 10 and 89. Okay, so what's going on here? It's the two halves are, one is 10 and the 89, and they both are 9's complement of each other. So 10 plus 89 is 99. So 1 plus 8 is 9, 0 plus 9 is 9. First half is 1 0, second half is 8 9. The two are 9's complement. Okay? So as soon as I know that the 9's complement, these two must have come from multiplication by sequence of 9's. Okay? For that you can watch the video, see multiplication by sequence of 9's. And with the video is, this is the video link. Okay, let's continue. That means 33 squared must have a 99 in here, which is 33 times 33, which is 11 times 11 times 9, which is 11 times 99. And if you watch this video, from here you can say from 11 I got 10, and from 99 here I got 89, which is 9 minus 1 is 8, and 9 minus 0 is 9. Okay, let's continue. Let's continue with the square of sequence of 3's. So 3 square is equal to 111 times 999 equals 110889. 110 comes from 1 less than 111, and 889 comes in from all from 9 and last from 10 of 111. Okay, so it's all from 9 last from 10 of 111 is 889, and 1 less then 1111 is 110, and also 1 plus 8 is 9, and 1 plus 8 is 9, and 0 plus 9 is 9. Let's continue. Now 3 square is equal to 1111 times 9999, which is equal to 11108889. Continue. 3 square is equal to 11111 times 99999, which is equal to 4 1s, 0, 4 8s, and a 9. Okay? Now it's a 6 3's squared, which equals 6 1s times 6 9s is equal to 5 1s plus 0, and 8 5 8s, and a 9. Okay? Let's continue here. Here is a 7 3s squared is equal to 7 1s times 7 9s equal to 6 1s and a 0 and 6 8s and a 9. Let's continue. Okay, let's continue. The next section we would discuss squares of numbers ending in 5. Let's continue here. Look at how do you do that. A number ending 5 is given by 10 times n plus 5. Okay. These are numbers like n equal to 10 times n plus 5, and if I do a square of that and n squared, it is a plus b, and square of that is a squared, which is 100 n squared, plus 2ab, which is 100 n, plus b squared, which is 25. Let's continue here. So which is equal to, if I extract 100 n from the first two terms here, I get 100 times n times n plus 1. So if I'm trying to extract n plus 1s from here, I get 100 n plus 1. Okay? And then 25 is plus 25. Okay, so that is equal to n times n plus 1 and 25. We're trying to exploit place value systems here, because we are going to shift the left part by 2 to the left, which is multiplying by 100. Okay, so we usually say that on left I get n times n plus 1, which was the, okay, and then 25 on the right. Okay? And which I in fact I mean is on left it's 100 times n plus 1 plus 25. That's the answer. And so this is the correct answer here. 100 times n times n plus 1 plus 25, and 25 has 2 digits. If I multiply some number by 100, we got a 2 zeros at the end, and this 25 added slides right into those 2 zeros. So I can say that at 25 on the right and n times n plus 1 on the left. So okay, that's, we are trying to exploit place value system here. Let's continue here. Note, if n is 11, then n square is 100 times 11 times 12. Okay? If it's, we're trying to do a square of 115, so that is plus 25, and that is 13200 plus 25, which is 13225. That means that 115 squared is 13225. Let's continue. On the left, it's by 1 more than 1 before. This is the sutra we are going to use here. So this is n was the original number on the left. We say n times n plus 1 by 1 more than 1 before. On the right, it's 25. Let's continue. On the right, it is 25. Some examples now. 15 times 15. On the left, it's 1. 1 times 1 plus 1 is 2. And on the right is 25. So 15 times 15, 15 squared is 225. Okay. Next another example, 75 times 75, which on the left it's a 7 times 8. 8 is by 1 more than 1 before of 7. And on the right 25, answer is 5625. Continue. Example 135 times 135, on the left it's 13 times 14. 14 is by 1 more than 1 before of 13. On right is 25, and answer is 18225. Let's continue. 65 times 65, on left it is 6 times 7. 7 is 1 more than 1 before of 6, and so answer is 4225. Let's continue here. 245 times 245, 245 squared is on left 24 times 25. On the right is 25. It's a 625. Let's continue. 35 times 35 is 35 squared is on left is 12. On right is 25. 1225. 985 times 985, on the left is 98 times 99. On the right is 25. And so 98 times 99 is 9702, and on 25 on the right. Note, use basic base multiplication. This I used that To get 98 times 99, I can use the base multiplications we studied before, and that's the video for that. Let's do some of examples here. So do a fraction now. 0.25 times 0.25, 25 times 25 is 625, and there are two digits here after the decimal, 2 here. So I need to have 4 digits after the decimal, so that I need extra 0 here. So 0.0625. 20.25 is quarter. 0.25 is quarter. So 1/4 times 1/4 is 1/16th. So 1/16th is 0.0625. Let's continue here. We need 4 places after decimals. That's how come there's 0 here. Okay. Up 0.25 is quarter. So there again, just the 1/4 times 1/4 equal 1/16th, which is 0.0625. We just converted 1/16 to 0.0625. Okay, now 0.125 times 125, same way. It's on left is 12 times 13, and on the right is 25, and there are 3 digits here, and after here, so it's a 6. We have divided by 1 million here, and that is equal to 0.015625. 15625 from here, and 0 extra because 3 digits and 3 digits 6. I need 6 digits after decimal. These were 1, 2, 3, 4, 5. I make up that with extra 0 here. Let's continue here. 0.75 times 0.75 is 5625 after decimal. Okay. On left, 7 times 8, 56, and 25 on the right, and the 4 digits, I need a 4. And 0.999, 3 nines and 5, and 3 squared. Okay. So on the left, it's 999 times 1000, and on the, okay, which is 99900. 0. On the right, it's a 25. So 0.9995 squared is equal to 0.393025. Okay. Some exercises now. So 15 times 15, we already did before. 35 times 35, 45 squared, 55 squared, 65 squared, 75 squared, 85 squared, 95, 115, 125 squared, 145, and some more. Okay. Now some fraction. 0.25 times 0.25 we discussed already. 0.35 times 0.35, 0.125 times 0.125, 0.65 times 0.65, and some more. Okay. We're going to extend the method we just studied. Okay, here in this section we will consider product of two numbers such that neither of which ends in 5. Instead, sum of the digits on the right part is 10. On the right, sum is a base number like 10, 100, and 1000. So we would not be doing squares here. Okay. Left parts are equal. Example is 23 times 27. So we are not doing square, but we are trying to use same method, which is by one more than one before. Okay. Here two numbers are of this type are 10a plus n, and this is one number. Okay. And now there is 10a plus 10 minus n. Okay, so n and 10 minus n adds up to 10, which is one of the base numbers here. Okay. Continue here. Here two numbers from previous page, and one is 10 times a plus n, and n2 is 10 times a plus 10 minus n. Left part is constant, same, and right part is adds up to 10. N plus 10 minus n is 10. Let's continue here. N1 times n2 is first number, which is 10a plus n, times second number, which is 10a plus 10 minus n. 10a plus 10 minus n. Let's continue here. So we're going to multiply now. So I multiply 10a by 10a. I got 100a squared. I'm going to multiply 10a with the 10 minus n. This is what I got. 10a times parenthesis 10 minus n, parenthesis closed. Then I start multiplying with now n here. N times 10a is 10 times an, and I multiply 10 with it by 10 minus n, and that is the other term here. Okay. Let's continue. So we have 100a square plus this term gives me 100a, and 10a times minus n gives me minus 10n. We had a plus 10an, and this is minus 10an, and plus 10an, and the last term was n times 10 minus n. These two cancel out, and from here I can extract out 100a as a factor. So this term is 100a times a plus 1. So we have extracted 100a of a plus 1 from here. And then last term is n times 10 minus n. See the 100 here? If this thing is the 2 digits, we can use place value system to say this is the left hand part of the answer and this is the right hand part of the answer. Let's continue here. So on left side is a times a plus 1. On right side is n times 10 minus n. If this thing, if there are only 2 digits in the right part, this is represent 100 times of a times a plus 1. So we would exploit place value system when we can, but we have to honor its rules. That means we have to replace 100 by left hand, say we removed 100, say it's the left hand part, so that because we removed 100 from here, that dictates that we do need a 2 digits on the right. Let's continue the method here. So that means n1 times n2 is 10 times a plus n, and that's what the n1 times n2 was. Okay, so and this is the results was 100 times a plus 1, and on the plus n times 10 minus n. And 23 times 27 is 100 times 2. This is 2 right here. This was a, and this is the n, and this is 10 minus n. 2 and times 2 plus 1, which is it 100 times 2 times 2 plus 1 right here, and plus n, which is 3, and n 10 minus n is 7. 3 times 7. Okay, so we get a 600 plus 21, which is a 621, and this is 6 on the left and 21 on the right. We can say that instead of 600 plus 21, we can say 6 on the left and 21 on the right. As long as there are 2 digits on the right, and that's covered by this 100 multiplier here. Okay? So 100 multiplier on the left, 100 is the base here, and that's 6 on the left of 2 digits. It is like 600 plus 21 like we need. Okay, let's continue here. So that means that is 2 times 2 plus 1 on the left and 3 times 7 on the right. This is a by 1 more than 1 before, like sutra we have been talking about. Sutra is by 1 more than 1 before. We had departed from doing squares, but this is important because this uh, multiplication also uses same sutra. Okay? And these multiplications need to go together with the square of numbers ending in 5. Let's get examples. Say 21 times 29 is 100 times 2 times 2 plus 1 on the left, 1 plus 9 on the right. Let's continue here. So it's 600 on left and 9 on the right, okay? Which is 609, and that's like 6 and 09. 6 on left, 09 on the right, and which is a 2 times 2 plus 1 is 6, and 1 plus 9 is 9. But I do need 2 digits on the right, so that would mean that instead of 9, I would need a 09. Notes. One right become on the right 9 becomes 09. Okay, we love to exploit place value system, and we also need to honor its rules. Okay, continue here. So either use 100 times 2 times 3 plus 1 times 9, or use 2 times 2 plus 1 and on the right 09. Okay. Now 22 times 28, 24 times 26, 37 times 33, and some more. And these fractions now. 0.22 times 0.28, 0.998 times 0.992. Okay, let's continue. Here. So in this case, we'll consider example where left parts add up to 10 and right parts are equal. Let's continue here. So 3, 4 times 7, 4. On the left, it's a 3 and a 7. They both add up to 10. On the right parts, they are equal. See, it's not a square, but it is goes along, use the same kind of method as is used in square of numbers ending in 5. Okay? So let's see what, in this case, product is 3 times 7, the parts on left plus the common part on right, and that's left part. On the right, it is 4 times 4. So either use 100 times that on left plus the right part, or make sure there are 2 digits on the right. Let's continue here. So it's 21 plus 4 on the left, 16 on the right. It's 25, 16. So it on the left, it's actually 2500 plus 16, and because there are 16 has 2 digits, and we can say 25 on left and 16 on right. Continue. Okay, you can prove the assertion if you care to. Okay, and yeah, this thing works only for 2-digit numbers. If it's more than 2 digits, it doesn't work in exactly the same way as stated here. Okay, let's continue. 51 times 51, 52 times 52, those squares. Okay, 53 times 53. When it's 5 on left, these become squares. Okay. Then 27 times 87, these are not squares. 43 times 67, 77 times 37, 68 times 48, 73 times 33, and more. Now fraction 0.23 times 0.83, 0.41 times 0.61, 0.76 times 0.36. Okay, and some more. The next section is using base multiplication method. Squares using base multiplication method. Let's continue here. From base multiplication. Let's continue. Sutra for squares is double the deviation, which might be deficiency or surplus, and put the square to. So this is the, in simple words, it's we are going to double the deviation and put the square to. Let's see how we are going to apply that. So example, 98 times 98, base is 100, deviation is minus 2, and when we say from double the deviation, left hand side is going to be 98 minus 2, which is 96. And from the square of the deviation, we get RHS is equal to minus 2 times minus 2, which is a 4. Okay, let's see where do we go from here. Okay, now if we want to export the place value system, we need to get a 0, 4 instead of 4. 98 times 98 is 96, 0, 4. Base is 100, and the detailed version of this base multiplication was left hand side, which is 96, times the base plus the right side. Okay, so that 9604. Okay, so I need 2 digits on the right because base is 100, which has a 2 zeros. When we multiply by 100, when I multiply 96 by 100, I get 2 zeros. So this 4 on the right has to fit within those 2 zeros. That is 0, 4. Let's continue here. 98 times 98 is 96 times 100. That's another form. Plus 4. Base times the left hand side plus the right hand side, which is 9604. Let's some more examples here. 99 times 99 is 98 and 01. So 9801 is the answer. Okay, so let's continue that one. 80 and 80. Let's take a base of 100. 80 is deviation is minus 20, so it is double deviation. 80 minus 20 on the left and 20 times 20 on the right. Let's continue here. Let's square of the deviation here. So 80 minus 20 is 60, and then multiply by base of 100, it becomes 60 and it's two zeros, and 400 on the right is a plus 400, that gets me 6400. So 80 times 80 is 6400. Let's continue here. Need that we only need two digits on the right to exploit place value system. The leftmost 4 must be carried to the left hand side. Okay, left. From the right hand side there are 400 here, the 4 must be carried to the left hand side. Okay, so it was 60 on the left, 400 on the right, the 4 get carried to the left, becomes 64. Okay, let's continue here. That's 103 times 103. So here's double the deviation. 103 was the deviation surplus plus 3, so we double that, become 106 on the left and 09 on the right. So 103 times 103 is 10609. Let's continue here. Let's do 999 times 999. It's a 998001. So here is the deficiency or deviation was minus 1 here, so we make it minus 2. Base was 1000, so make it 998. 1000 minus 2 is 998, and 001, which is the deviation, was minus 1. Minus 1 times minus 1 is a plus 1, and I need two more zeros, because when I multiply 998 by the base 1000, I get three zeros, and this 1 has to fit in those three zeros. So that is a three zeros, three digits here on the right. Okay, let's continue here. So if I say 1015 times 1015, so 15 is deviation plus 15. Double that, become 1030. Base is 1000, and on the right it's a square of 15. 15 times 15 is 225. Three digits. I need three digits here, because 1000, when I multiply left by 1000, I get three zeros, and this 225 has to fit in those three zeros. So just fine here. So 1015 times 105 is 1030225. Let's continue here. Example 87 times 87. So let's consider base of 100. So minus 13 is the deviation. Double that, I get it a 100 minus 26 is 74. On the right, it's a 13 times 13, 169. Only need two digits on the right, because base is 100. When I multiply 74 by 100, I have a two zeros, and this thing has to fit within those two zeros. So this one get carried to the left. So answer is 7569. To square up. Now we are going to do a proportional based numbers. We were so far using 1000 and 100 as a base, which are natural based numbers. Now we will consider some proportional based numbers. The sutra we stated before applies to numbers close to natural based numbers. Natural based numbers are 1, 10, 100, 1000, are on the fractional side 0.1, 0.01, etc. Let's continue here. With slight modification, we can extend the application to more squares. Okay? So for numbers close to a proportional based number, the extra step is, after doubling the deviation, we multiply left hand side by proportionality, and this proportionality may be 1. That's what happens in the case of using natural based numbers. Okay, let's do some examples here. First example is 52 times 52, and here is the part we are going to, base number we are going to use 50, deviation is plus 2, 52 plus 2, that's twice the deviation here, double, so become 54, and here is multiplied by proportionality, because 50 is a 5 times the base 10. Okay, so we get 52 plus 2, 54 times 5 on the left. On the right it is say 2 times 2, 4. Only one digit is allowed, because 50 is 5 times 10, and base number 10 has a 1 0. Okay, so it's on the left, it's a 54 times 5, which is 270, and plus on the right it's a 4. So it's a 2704. Let's continue here. So for 198 times 198, base is 200, which is 2 times 100, and deviation is minus 2. So double the deviation gets me 196. Multiply that with the proportionality 2. On the right, I got 0, 4 here because base is 200. 200 has two zeros, and this 4 has to fit within those two zeros, and that's 0, 4. Okay, so answer is 39204. Let's continue. Example 82 times 82. So if you take a base of 80, which is 8 times 10, deviation is plus 2, 82 plus 2 is 84, and multiply by proportionality, which is 8. So 84 times 8 is on the left, and 2 times 2 is a 4, 4 on the right, and base number is 80 has one zero, and this 4 has to fit within one zero, so only one digit is required. So it is 6724. Let's continue here. 222 times 222, which is a base number is 200, deviation is plus 22, so double deviation get me 244 here, and there is a proportionality 2. So that's on left we have 488, on the right it's a 22 times 22 is 484, but I only need two digits on the right, so this 4 on leftmost 4 of the right hand side gets carried to the left. So answer is 49284. Let's continue here. Example, you can also do that. 222 times 222 is 4 times 111 times 111, and 111 is 12321. Okay, you can do either use the sutra we're just trying to do that is okay, that's using a proportional base numbers, or you can say that 111 by 111 is 12321. This is symmetric here. Okay, 123 and 1321. Okay, so one you can multiply that over here. 123 times 4 is 492. 21 times 4 is 84. Okay, you have already seen numbers like this before. 1111, times square of ones is 1 2 3 4 3 2 1, like that. Okay, and 5 ones is that, and so on. Example 2015 times 2015. So 2000 is base, plus 15 is deviation, so double the deviation get me 2030. Proportionality gives me plus 2 times 2, and on the right is 225. Three digits on the right is fine here because base here is 2000. 2000 has three zeros, and this 225 need to fit it within those three zeros. That's fine. So I got 4060, 225. 2015 times 2015 is 4060, 225. Let's continue here. Example 708 times 708. It's a base number. Proportional base number is 700, which is 7 times 100. Deviation is plus 8. So double deviation get me 716. Multiply by proportional to get me times 7. On the right it's 8 times 8 is 64. I need two digits, and I have two digits here. So answer is 7 times 716 on left is 5012, and 64 on the right. Let's continue here. 396 times 396. So it's a base is 400. Deviation is minus 4. So it's a double deviation get me 392. Multiply by proportionality 4. 4 times 392 on the right. It's a 4 times 4, 16. I need two digits. 400 has two zeros, and this 16 has to fit within those two zeros. So answer is 1568, 16. Let's continue. Yeah, 4 times 392 is 1568, and this is 16 here. Let's do the exercise. 11 times 11 first exercise. 89 times 89. 99 times 99, and so on. Okay, some more. Here is the proportional base number: 22 times 22, 38 times 38, 76 times 76, 203 times 203, and some more. Next section, please. And in this section, we would discuss squares using some formulae. Let's continue here, and use squares using formula. Okay. And basic formulas are a plus b, square of that is a squared plus 2ab plus b squared. Square of a minus b is a squared minus 2ab plus b squared. Okay, and a plus b times a minus b is equal to a squared minus b squared. Okay, if you are not too familiar with the algebraic notation, just think of that this is one number and it's another number. Okay, and you can compute a plus b squared using vertical and crosswise, and you can do same thing, method of multiplication. So you can multiply a minus b times a minus b using vertical and crosswise. Similarly, you can multiply a plus b times a minus b using vertically and crosswise multiplication and to get the right hand side. Use a formula usually means that we are going to evaluate left hand side in terms of right hand side. Okay. In third one, we will do a little bit manipulation. We will try to compute a squared using rest of the terms in the equation here. Let's continue here. How do we use the formula? We evaluate left hand side in terms of RHS, right hand side. Okay. Okay. So let's compute 110 times 110. So 110 is, we would apply this formula here. 110 is 100 plus 10. So this a squared is 100 squared right here. 2ab is 2 times a times b, and here b squared is 100. Okay. So we got an a, that is 12100. Okay. We also could do that using base multiplications. Okay. Let's do example here. 75 times 75. By addition and by subtraction, we change 75 to 100 minus 25 times 100 minus 25. A is 100, B is 25. Okay, so we would do that. A squared is 10,000 minus A twice the A, 200 times 25 minus 5,000 plus B squared plus 625. Okay, let's continue here. So that's 5625. 10,000 minus 5,000 is 5,000. 5,000 plus 625 is 5625. Let's continue. Let's do another way. So instead of doing subtraction here, let's do 50 plus 25. So split 75 into two parts, 50 and 25. 50 plus 25, that's 50 plus 25 squared here. Okay, so that is a squared. A is 50 and a squared 2500. Now 2 times a is 100 times b 25. 100 times 25 is 2500. Then b squared. B squared 25 squared is 625. So 2500 plus 2500 is 5000 plus 625. Okay, so that's a 5625. Let's do another example. 711 times 711, which is 700 plus 11 squared. Okay, so a is 700, b is 11. So a squared is that 49 with 4 zeros at the end. 2 times a is 1400 times b 11. 1400 times 11 is 15400 plus b squared. B is 11. 11 squared is 121. Okay. Now let's add them together. 49 and 4 zeros at the end plus 15400 is 50400. It's a 505,400 plus 121. So it's 505,400 plus 121, which is 505,521. So examples continue. Let's do some more example here. Now we're going to use the third formula here, which we have not used so far. Okay, we will rewrite this formula here which a squared is, left this side here, a plus b times a minus b plus b squared. So it's a plus b times a minus b plus b squared. We want to evaluate a squared. We're going to find small b such that I can compute a plus b times a minus b easily, and then add square of the b we just computed. Okay, let's figure out. If you can find a b which simplifies right hand side, we can find a squared. Okay, that's what we're trying to do here. Example 74 times 74. So we can do 74 plus 6, which is 80. I can multiply a number by 80 easily. Then I had to a minus b here. 74 minus 6 plus 36. Okay. So see, this is a plus b. I found a b of 6, and this is my b squared, this is my a plus b, and this is a minus b, and this is what I'm trying to solve here, okay, which is equal to 80 times 68 plus 36. So let's try to multiply these now. So if you multiply 80 times 68, so 8 times 8 is 64, there's 4 here, and 8 times 6 is 48 plus the carry 6, 54. 5440 plus 36, that's a 5476. Let's continue here. If you want to see that 74 is, we were doing 74 times 74, we multiply these two numbers together, and you will notice that 74 is average of these two numbers. 80 plus 68 is twice of 74. Okay? So you can also compute 74 times using this formula here. You can compute 74 times 76 like 75 minus 1 times 75 plus 1, and that 75 we got is average of these two numbers here. That will get you 5625 minus 1, which is 5624. Okay, let's continue here. Now let's do exercise here. Find squares. Here's the first number, 1089, square of 507. Next, 904, 891, and some more. Into next section. Let's see what we're going to do here. In this section, we would find squares using duplexes. And duplexes come from vertically and crosswise multiplication method. Let's continue. Duplexes are, what's a duplex? When we multiply a number n by n, which is itself, duplex is raw result in a column. Okay, by raw I mean that it may have multiple digits and we still need to resolve the carry part. Okay, so duplex is raw result in a column. Okay, let's continue here. So let's go over say what numbers look like. Our decimal number system, AB, sum of AI, which is coefficient, times the corresponding base, which is 10 power I, for I is in 0, 1, 2, 3, and so on. Okay. Note that I did not consider a negative values for I, but the analysis holds even if you have a negative values of I here. Okay. Let's continue here. Note that we are dealing with whole numbers at this time, and the analysis does extend to decimal fractions. Okay. So 0 is the lowest index or exponent of the base number 10. So that tells me that this number a is a whole number. Let's continue here. So a times a, so we will be multiplying it one a by another a, and in the multiplication we multiply one digit from multiplicand, another digit from multiplier. Okay? And digit is AI, and the position place value of that is given by 10 power I. Here coefficient value of that digit is AJ, that's his nominal value, and that's the place value multiplier is 10 to the power j. Okay, let's continue. We would be taking sums for a digit k equals 0, index k equal to 0, 1, 2, 3, and so on. Again, 0 is the smallest value for k of k, that we still say we are getting a whole numbers as a result, where k is I plus j. Okay? So we'll be grouping these sums for various values k. For k, we'll get a one sum where I plus j is 0, and k is equal to 1. We will get another sum from terms multiplicand like the ai plus aj, ai times aj, such that I plus j is 1, where either if I is 0, then j has to be 1, and if j is 0, then I would have to be 1. Okay, let's continue here. Okay, now just repeat that from the previous slide. Okay, this a times a would be some of these terms like this, where k is 0, 1 in k is a non-negative integer starting from 0. Let's continue here, where k is, and k is given by I plus j. I is the coefficient ai, and I is the index or power of the base number 10 here, and j is the base power of base number 10 in the second term. Let's continue here. In the above, ai is the coefficient of 10i, 10 to the power I from multiplicand, and aj is the coefficient of 10 to the power j from the multiplier. So this term comes from multiplicand, this terms come from multiplier. There are two operands in multiplication, so one of they're both same values here, so one of them is multiplicand and the other is multiplier. Let's continue here. Above sum can also be written as, so we can combine these two products here and take out the multiply coefficients together and add up the powers. Okay. Okay. We usually concern ourselves with the ai times aj, where place value system takes care of the exponent part, which is 10 to the power I plus j. Here 10 to the power I plus j. We usually multiply ai and aj, and place them in right position such that which takes care of the exponent part. 10 to the power I plus j is the exponent part. So duplex, again, I just repeated that from previous slide. Okay, so here is I'm going to start working on an example here and go over, see how we compute duplexes here. In the units column, which is 10 to the power 0, so with the coefficient index of the 10 is, our power of 10 is 0, and the contributors are, here the example here, a b c d times a b c d, so the 4-digit numbers, and only 2 digits that can contribute to this product here are d and d, so one column on the right. Okay, and so we will multiply d by d, and that's the only product we have, and sum of the such products would be d squared, so that's d squared, and in notations we call that's a duplex of d. So d was involved here, duplex of d is d squared. Where we got d squared from? Multiplying this 2 digits in the units column here. Okay, and where they go in units column of the result. Okay, let's continue next column here. Now we are on a tens column, which is a power 1 of a 10. Okay, in that column results come from this multiplication or this multiplication. So when you multiply this by this is units place and this is tens place. I got a value which is tens place. If this tens place digit, and this is one units place digit. When you multiply these together, I got a result in a tens place value. Okay, so here is a CD and here is another CD. So we have a 2 CD. Here they were vertically aligned together. I got D squared. We multiply them together, we got D squared. Here they are crosswise aligned together with the products were crosswise here. We get 2 CD. Let's continue here. So I get 2 times CD, and what 2 times CD is? It's a duplex of CD. These are CD here. We would, when we try to compute squares, we know that the multiplier and multiplier are the same values. So we just use the operand here, and so we say CD were involved here, CD were here, so duplex of CD is, the notation is duplex CD is 2 times CD, and that's the product of this product plus this product. Let's continue here. Our next column, 10 to the power 2 column, which is 10 to the power 2 is 100, and the contributors are, we can get product from here, which is B 100 times 100 times D, or D times B, B is B times 100. Okay, these are tens column here, or add this C and times C. Okay, so this product in 10 square column is BD plus BD, which 2BD plus C squared. Okay, so that is this product BD plus BD is 2BD plus C squared. So C squared here, and notation is that's a duplex of BCD. BCD here, duplex BCD here. When the pairwise term, pairing terms were crosswise, we got 2BD. When pairing term is vertically, we got C squared. Pairing term vertically, multiply them together, get D squared, only 1. Pair them crosswise, then CD, we got 2CD, because there are 2 pairs here. Same thing here, we pair crosswise, BD, BD. There are 2 pairs, it's 2BD. And pair vertically, it's a C squared. Okay. Let's continue, next column. Here is my 10 to the third column, which is 1000. Okay. In 1000, I'll need all these participants, every digit contributes. So we got AD plus BC plus BC plus AD. AD here and AD here, 2AD. BC here and BC here. This is a crosswise. AD is crosswise, I got 2AD. BC is crosswise, I got 2BC. So sum in the column is there are 4 parts being added here. There are 4 parts. AD here and AD here. AD plus AD is 2AD. BC here and BC here. BC plus BC is 2BC. Okay, and we call, what we call this thing? We call that is a D of ABCD. That's duplex of ABCD. ABCD were contributing elements in our columns here in this product. So we call duplex of ABCD is 2AD plus 2BC. A and D, that's 2AD. B and C, 2BC. Let's continue. So next column is 10 to the power 4 here. Okay. Okay, let's see now who are the contributors. This units place does not contribute anymore. Only 3 digits contribute ABC. So here AC and plus AC plus B square. That's 2AC plus B square. Here is crosswise. That's twice to that. And here is a 2 times that. And here is a vertically single 1 times that. Okay, so that is equal to 2 times AC plus B square. And that is a duplex of ABC. Let's continue. Okay, so we already have so far gone done that far in the previous slide. Let's continue. So on 10 to 5th power column, which is a 100,000. Okay, and only these 2 digits contribute. Okay, These are contributors here. We continue here. And so that means AB crosswise and AB crosswise. When crosswise, you have twice that. So column sum is 2 times AB, and its notation we call that's a duplex of AB. Okay, let's continue here. So in that 10 to the power 6, that's a millions column, and contributors are it's only the leftmost column here, A times A. Okay, A and A are vertically aligned, so it's A squared. Only product and once only once. Okay, so A squared. Let's continue, and we call that duplex of A. Let's continue. Okay, so we got all of them. When it is a one column, DD vertically D square. When it's a two columns and crosswise, 2CD. And here this is crosswise 2BD and is vertically C squared. Okay. Here's crosswise 2AD and crosswise 2BC. Here's a crosswise 2AC and here's vertically B squared. Here's the crosswise AB, that's 2AB. Okay. Here's the vertically A squared. Let's continue. Observations. Okay. We make pairs from for multiplications. Okay. We start pairing from outermost digits. Okay. Then add and continue to move inwards to complete pairing. In a crosswise situation, we use twice the product. In a vertical situation, we use one time the product. Let's continue here. Note, in a crosswise situation, two digits in different positions make a pair. In a crosswise situation, two digits in a different position make a pair, and that gives me twice the product. In a vertical situation, two digits in the same position make a pair, and that gives me one time the product. Let's some examples for duplexes. Here's the first example: D of 5, duplex of 5, which is only one term, which is this 5 times 5, 5 squared, and we use only once of that. So I should be skipping one times because this is just to tell you that it's only one product here. 5 times 5 is 25, and that's what it is. Okay. We have now two digits here, and they are in two different positions, so we did twice of the product. 1 times 3 times 2, 2 times 1 times 3, twice of that product is 6. Okay. In 79, the two digits in two different positions, so we got twice the product. 7 times 9 is 63, times 2 is 126. 7 times 7 times 9 is 126. Okay. Here 441, and there are pairing pair this 4 with the 1, which is different positions, so that's 2 times 4 times 1, and this 4, middle 4 we pair with the same another 4 in same position, which is a 4 times 4. So this is 8 here and 16 here is 24. Let's continue. 190, we pair 1 with 0, so 2 times this twice, and there is single 9, pair 9 by itself, that's 81. Okay, so let's say duplex of 190 is 81. Let's continue. 365, we pair 3 with a 5. 5 is in different position than 3 is, so we got twice the product. 2 times 3 times 5 is 30, and plus 6 is the same position. We pair with 6 in the same position, that gave me 6 squared. Okay, so 30 plus 36 is 66. Let's continue here. Now we got a duplex of 4371. We pair 4 with the 1, which is in a two different positions, so we got twice the product. 2 times 4 times 1 is 8, and we pair this 3 with the 7, and the 2 are in different positions, and it's a twice the product. Twice times 3 times 7, so it's 8 here, and 2 times 3 6 times 7 is 42. 42 plus 8 is 50. Continue here. Now we have 5 digits here. 5 2 9 5 2 1. We pair 5 with outermost 1 here. Two different positions, we get twice the product. 2 times 5 times 1. We pair this 2 with this 2 here. There are two different positions, so we get 2 times 2 times 2 for that position, and this we got lone 9 left. We're going to pair 9 with itself, and they get 9 times 9 is only once. Okay, so this 10 here, 8 here. 10 plus 8 is 18. This is 81, and plus 81 is 99. Okay, 99 here. Let's continue. Here is another one, 19086, the 5 digits again. We pair 1 with a 6, that's different positions. 2 times 1 times 6, that's contribution from that. 12 here. Then we pair 9 with 8, which is 2 different positions, and its contribution is 2 times 9 times 8, which is 144. Then 0, lone 0 here, we pair with itself, that 0 times 0 is 0. So it's 12 here and 144 here. 12 plus 144 is 156. Let's continue. Let's do another example here. D31172. We pair 3 with a 2, which is a 2 different positions. So we get twice the product. 2 times 3 times 2 is 12. We pair this 1 with the 7. There are 2 different positions. So we get 2 times 1 times 7. That's 14 here. Then we got lone 1 left here. We pair that with itself. That's 1 times 1. Okay. So this is 12 here, 14 here. 12 plus 14 is 26, plus 1 is 27. Let's do some exercises now. Find duplexes for the following numbers. Okay, 33, 44, 56, 75, 98, 76, and some more. Now, 3-digit number 368, 700, 161, and some more. Now, 4-digit numbers 1368, 859, and some more. Now, 5-digit number 60075, 49196, and some more. Let's try to find what we already did duplexes now, and we were trying to do squares. Let's see how do we make it squares from a duplex. Let's continue here. Observation: we got duplexes from square. See, when we did the table over there in a few slides before, a times 8, we were trying to do a times 1, a, and we got the duplexes. Duplexes are column-wise raw multiplication results. Okay, we have to resolve the carries. Caution: duplex may have multiple digits, except for leftmost position. We can only have one digit in the result column. A duplex may have multiple digits. This becomes raw multiplication results, and we allow multiple digits only in the leftmost position. And I'm assuming that we are going to take the carries to the left. We can have only one digit in the results column. Okay, we need to resolve these carries to get the square. So that's the here. So d of 3 times 3 is 3 squared. D of 3 is, which is d of 3, which is 9. Okay, that's it. That's my answer here. No carries to worry about. Okay, that. And let's continue. Another example. I've got 71 times 71. First, I do a one column, which is a d of 77. That's d of 7. As we do d of 7. Then we do a 2 column, d of 71. Then we do 1 column, d of 1. Okay, that is equal to 49. 7 times 7 is single digit here. That square of that is 49. And it's 2 digits here. 7 times 1 times 2 is 14. And here is single digit here again is 1. Let's continue here. So result is this carry comes back here, make it 50 here, come to the left. So I go 5041. 71 times 71 is 5041. Let's continue. So let's do a 3 digits, 395 times 395. So first we do a duplex of 1 digit, 3, then duplex of 1 more digit, 39, then duplex of all 3 digits, 395. Then we start dropping columns here, duplex of 95, and drop 1 more column, duplex of 5. Okay. So in the leftmost column we have duplex of 3, and next column to the right, duplex of 39, column to the right, duplex of 395, column to the right, duplex of 95, and units place, duplex of 25. Let's continue and resolve these numbers here. So that's 9 here, and 3 times 9 is 27 times 2, 54. Here is a 2 times 3 times 5, 30, plus 81, 111. Here is 95. 9 times 5 is 45, times 2 is 90. Here is 5 squared. 5 times 5 is 25. Okay, let's continue here. So let's start taking resolve the carries here. use this carry here. This is 90 here. I make a 92 here. Okay, and rest of them are the same. Okay, now here is a carry 9. Have a 1 here. I make a 120 here. Okay, 111 plus 9 is 120. Okay, let's continue here. Now I take the carry 12 here. 54 here. 54 plus 12 is 66. And now take this carry 6 here, add to 9, 6 plus 9 is 15. So got 15, 6, 0, 2, 5. Let's continue here. So 395 times 395 is 156,025. Let's some more examples here. Example is 7952 times 7952. That's the square of 7952. Okay. Now start doing the duplexes. Duplex of 7 on leftmost is 49 column, and then duplex of 2 digits 79 is 7 times 9 is 63 times 2 126. Now duplexes of 3 digits now 795. 2 times 7 times 5 is 70 plus 81. That's 1. It's 7 times 5 is 35 plus times 2 170 plus 81, that's 151. Now 4 digits, 7 times 2 is 14, times 2 is 28, 9 times 5 45, 45 times 2 is 90, 90 plus 28 is 118. Now we got in a 3 digits here, 952, 2 times 9 is 18, 18 times 2 is 36, plus 25, that's a 61 here. Now 2 digits here, 2 times 5 times 2 is 20, that's 20 here. The last digit left here, 2 times 2 is 4. Okay, so let's try to resolve the carries now. This 2 gets carried to left, the 61 become 63. Let's continue here. So that's 63 here. Now 6 gets carried to the left, the 118 becomes 124. Let's continue here. Now 12 gets carried to the left, so 151 becomes 163. Now 16 gets carried to the left, so 126 become 142. Okay. Now 14 gets carried to the left, 49 becomes 63. So answer is 63234,304. 7952 square is 63234304. Let's do this exercise now. Find the square of the following numbers. Okay? 54, now 2 digit numbers, 67, 68, some more. Okay? Now 3 digit number 575 and some more. 4 digit number 2679 and some more. 5 digit number 76501 and some more. Okay, that's it. Let's look at references here. Okay, first reference is Vedic Math Teachers Manual, Volume 1, which is the elementary level by Ken Williams. You can get that in PDF form for free or print form for purchase from vedicmaths.org. Next reference is Vedic Maths by Bharti Krishna Tirtha ji, and that is my main reference for the topic. Let's continue. Next is Vedic Maths for Schools in 3 volumes and by James T. Glover. Mr. Glover uses these books in his school, and they cover lots of topics including some geometry which I don't cover. Okay, let's continue here. Vedic Math for All Ages by Vandana Singhal is a good book, easy to read and cover most of the topics. Okay, let's continue here. Then I have a Figuring by Shakuntala Devi. Its whole title is Figuring the Joy of Numbers by Shakuntala Devi. I have used that exclusively in the first section of this video. Okay, that is it.